The end is near. Class number 25. The next class, class 26, is going to be a course review. So this is the last topic of the semester, and I thought it would be good to cover something that's an important fluid mechanics topic, and those are going to be turbomachinery turbines. We covered this a little bit in class 14, and I'll make some references to that. So here's a cartoon. I had this from class 14 already, where we had wetted discharging the CO2 and causing a reaction that created angular momentum, right? So that's the idea here for fluids, that we can use this angular momentum and turn it into torque, which creates power, and that's what we're doing with turbines. And I would consider, maybe I would call this more of a impulse. Maybe it's more of a reaction turbine. We'll see in a second that we have these two broad categories, at least of most turbines, of either impulse or reaction turbines. So I tried to create another one here where this is more of a water wheel, and I guess I would call this the impulse, and then this would be the reaction. And we'll talk about the distinction between those. But we have a jet or a nozzle that's spraying wetted onto these blades and causing a rotation, and which will cause a torsion, which could be used to develop power. So turbines from class 14, you'll recall that we used the Reynolds transport theorem as it's applied to angular momentum, and we had this outlet and inlet. And so I just put this up here because that's one of the visuals or examples that we first came in there, where you could see that we have that m dot times v, and if you recall from linear momentum, that created a thrust or a force, but now if we multiply it by an r, that's going to give us this torque right here. And so a more simplified equation that we would write for this is simply that R times m dot v. Some important things to note is that we want to make sure that it's just the right velocity to use there, because this velocity needs to be perpendicular to this radius. And so here's the Euler's turbine equation as written in chapter 14, but here is it how they've written it in chapter not chapter 14, in class 14. I believe it was actually in chapter 6 that we had it, and here's how they're writing it here. Now here's a note. I think I took this right out of Sengel's, where he says we must be careful of negative signs, since this is an energy producing rather than an energy absorbing device, and therefore for turbines we switch what we consider point 2 and point 1. So in this case, point 2 is the inlet and point 1 is the outlet. That's different from pumps, where we had point 1 was the inlet and point 2 was the outlet. But because pumps absorb power, and turbines create power, or not create power, they produce power, I guess. They transform the power from a hydraulic power into a motion power, rotating power. We switch what we consider the numbers. So there's the two basic types of turbines, and so we start with an impulse. And this is an example right here of an impulse turbine, where we have these nozzles, and there's a pressure drop across this nozzle as it increases the velocity, right? So we were doing that Bernoulli trade-off again between velocity and static pressure. So the static pressure drops down across the nozzle, but the velocity has increased. But there's no pressure drop across the moving blades, right? So we're going to think of nozzles and blades as two separate things. right? And they're easy to tell right here on the inlet, but right here, this fixed, what we call a stator, these are fixed blades, and I think of them as being nozzles, because you can see that the throat area is changing across these fixed blades. These not, and that makes them effectively nozzles, and they redirect to these moving blades right here. But you can see that the throat area does not change across this right here, right? So whereas there is a velocity drop, that's actually kinetic energy being taken out of the fluid and put into the moving blades. But there's no pressure drop across these. So no change of velocity magnitude across the blades, only a change in velocity direction. So they're saying absolute velocity. I guess that's, yeah. Again, that's actually, I'm not sure about that statement right there. There's no change of velocity magnitude. I'll guess, and it seems to me that I want to rethink that statement. Trying to think about that again. But there's no pressure drop across them, that's for sure. And the reaction turbine is different from that. So there is a pressure drop across not only the nozzles, but also across the blades. Right, and there's actually some amount of area change that's taking place. So this really relies, this pressure drop causes a reaction, which is part of the reason why the turbine is spinning right there. So it's really, there's a velocity, there's no pressure drop across the blades in an impulse turbine, but there is a pressure drop across the blades in a reaction turbine. And so that this is a way to look at them. Okay, so here is the breakdown for using Euler's turbine equation for an impulse turbine, and that is this Pelton type. Now, if you go back to our what we did in class 14, you could see that we covered in a bunch of different, I had a bunch of different examples. So we're going to cover another example, but here's an example, here's videos that we have in class 14. And so example 6, I think it's this one right here. That's the Francis. Here, all right. Example 7, video 7, which I think is example 6, right? Example 6 is video 7. That's confusing right here. Here is a Pelton turbine. And let's see, I'll minimize that. So here is the velocity triangle parallelogram. And you could see that we have this velocity coming, the inlet velocity right here. So that it's a relative velocity right here. See, here's we want the tangential component, by the way, up here. So the inlet is number 1 in this case. Is that true? I think we want to say... I think the outlet should be number 1. What do we say up here? 0.2 is the inlet. Okay, so I was wrong. So velocity 1 should be the outlet. And so it's going to be this relative velocity right here. Yeah. And we have velocity 2 is okay, I got it straightened out. Sorry about that. All right, so remember here that this is the inlet. So it's always going to be the actual velocity, not the relative velocity. That's where some confusion can take place, because we draw these parallelograms or the velocity triangles to account for relative velocity, right? So in terms of the okay, so this V2, remember, this is the inlet, and therefore the inlet, the actual inlet, is just going to be Vj, right? Because that's what is being moved into here. So the inlet is Vj, the velocity of the jet. But then we start to move into what is the relative velocity, and that's where we become confusing. Here's the close-up of this. So for relative velocity, because the blade is moving at an r omega as it's spinning, right? So that's going to be the velocity of the blade. And so the inlet is going to equal the outlet, relatively speaking, right? So there's the relative velocity inlet. And because this is a double-sided thing, which you might even want to just like kind of look only at half of this right there. So we could say that what we're really looking at is 1/2 Vj minus r omega on this side of it, and on the other side we have a mirror image, and so the outlet has to be 1/2, right? We're saying, because conservation of mass, we're going to have the inlet on this side of this, it's going to be equal to the outlet on a relative motion basis. So here is the velocity coming out, all right? And so it depends on this beta. You could just think of this beta in one respect as it could possibly be 180 degrees, and that would mean that this thing was coming out exactly the opposite direction of the inlet. So what they're pointing at right here is the velocity 1 and the tangential, which is the thing that we want right up here, is going to be this little vector right in there, right? So what we've done is we've taken the velocity of the jet right here and subtracted out here. So this is really what the relative velocity motion that the thing is experiencing, but here's the outlet of the piece, and then but we're also multiplying by the cosine of beta to account for this portion right there, right? So we're subtracting out those two, and of course this is likely to be a negative number because it's greater than 90. So it's really reversing it. So what we're going to have, we have a positive here, and we're going to end up having a positive right here. So this might be. No, I think that's going to be a number right there. So it's going to be, we could have this could result in a negative value. Yeah, okay. So that's this portion down there, right? We're subtracting out because we have that R1 plate. No, actually it got moved out to the outside over here. Okay. Yeah, because both the R's match onto the thing. Yeah, so this is what results from the math in there. So this is a Pelton type impulse turbine. I think I got that correct. And this is all about the velocity triangle again, just like it had with pumps. A little bit more of a straightforward, but not necessarily straightforward example here is now the Francis type reaction turbine. Right, so we had seen that previously in this video right here, which was video 6 from class 14, where we had an example of another example of a Francis turbine. We'll do another example after this of that. And here's a velocity triangle on the inlet. Again, remember the inlet is now going to be 2. Right, so this is the inlet, and then this is the outlet right up to there. And the velocity triangles get pretty small, but you can see that the relative velocity is now going to be related to the angle of this blade right in here. So we're going to have this V2T is going to be equal to omega R2 minus the normal. And just like what we had with pumps, we could find what those normal velocities are going to be using the flow rate coming in through the perimeter. So only the perpendicular portions of that do we consider the V. Is that true? Yeah. Okay. So they're showing it over here, but I would have placed it right in there, right here. But they're saying this is the, you can notice that they're perpendicular to the tangential, so that's definitely going to be right in there. And then for the inlet, or not, this is the inlet. Number 2 is the inlet, and number 1 is the outlet. That's coming towards the inside of this Francis type turbine. We can find the tangential velocity from this relation right there. And once again, we can find these by having a relationship which is going to be well, let's just write this out here. It's going to be equal to the 2 pi times the radius times what we could call B. You can see that B right here, B1 or B2, depending on what here, times V N, right? So whether it's the inlet or the outlet, we'll decide here, right? So this could be like 1 and 1, and so this is going to be 1 right there, or we could find it this way right here. So we get V2N, right? So we can work that backwards. And so using that, and then what this beta is going to be, and the beta is really related to the angle of these of the inlet and the outlet of here, right? So you can see that beta 1 and that beta 2 is related to its angle with the angle that way with the angle of this inner blade, right? Or as they're calling it, runner blades. Yeah, these runner blades, you can see how they're angled, and it's measured with, measured against tangential. So I'll do an example in the next video, or an additional example in the next video right here. I'll do that example.